shown below, the Thevenin's voltage, Thevenin's equivalent across the terminals A and B is. If we are looking from, while calculating the Thevenin's resistance, we have to look from the into the terminals A and B. At that time, we have to open the all independent voltage current sources as well as short circuit the independent voltage sources. If we do that thing, we will get Thevenin's resistance as infinite. Again, in order to decide the Thevenin's voltage, we cannot decide because the voltage across an ideal current source is not determined. So it's not possible to obtain the Thevenin's voltage equivalent across the terminals A and B. So option D is correct. For the 4-bit DAC shown in the figure, the output voltage V0 is. Here V0 is calculated as -4 into 1 by 16 plus -2 into 1 by 8 plus 1 into 1 by 4 plus -1 into 1 by 2 into gain is -4. So this is -1 by 4 -1 by 4 plus 1 by 4 -1 by 2 into -4. So it is going to be -3 by 4 into -4. So it is going to be +3 volts. That is option B is correct. Network shown in the figure, let the transmission parameters of the two-port network is TA and TB are the transmission parameters of the network NA and NB respectively. TA is given as 1341, TB is given as 1341. So the connection is a kind of a series connection, so that the complete network Z parameter matrix is nothing but addition of individual Z parameter matrices. So in order to get whole Z matrix, we have to convert individual network T parameter matrices into Z parameter matrices. That is, TA is converted into ZA, TB is converted into ZB, then all Z is equals to ZA plus ZB. Here ZA is equals to 1 by 4 and 1 minus 12 divided by 4, 1 by 4 and 1 by 4. Here ZB is equals to 1 by 4 and 11 by 4 minus 11 by 4, 1 by 4, 1 by 4. If the total matrix Z is equals to addition of these two, so it is 1 by 2 minus 11 by 2, 1 by 2, 1 by 2. That is option D is correct.
Okay, he has given a air blast circuit breaker is designed to interrupt a transformer magnetizing current of 11 amperes. He has given current as 11 amperes. Chops the current at instantaneous value of 7 amperes. Okay, that means the current it is chopped at every 7 amperes. If the value of LNC in the circuit is 35.2 Henry, okay, inductance is given as 35.2 Henry, whereas capacitance is given as 0.023 microfarad. Now we have to find the value voltage that appears across the contacts of the breaker. Okay, now what is the voltage it is going to appear across the contacts of the breaker? Okay, it is dependent on chopping current, not the total magnetizing current you have. Okay, if you see the voltage across breaker contacts at chopping is E is equal to, it is given as I into square root of L by C. Now what is chopping current? 7 amperes into square root of L by C is 32 by 0.0023 into 10 power minus 6, which is equal to 866 kilovolts is the answer, option D.
For the network shown in the figure, we have to find out the rate of change of inductor current at at the instant t equals to 0 plus, that is IL of 0 minus is equals to IL of 0 plus, that is nothing but 2 amps. So V is equals to, after opening the switch, the current direction in the inductor is not going to change. So V is equals to 2 into 20, that is 40 joules. But here the voltage across the inductor is VL, that is VL plus V is equals to 0. VL is equals to minus V, that is minus 40 ohms, which is 4 DIL 0 plus by dt. DIL of 0 plus by dt is equals to minus 10 amps per second. That is option B is correct. Consider a very lightly doped p-type semiconductor where P 4 greater than N is not valid. Then, using a Morse-Action law and the electric neutrality principle, the valid equation is. Here, electrical neutrality principle is nothing but a total positive charge is equals to negative charge. Number of holes and number of donor atoms is equals to number of electrons and number of acceptor impurities. Here this is very lightly doped p-type semiconductor, so Nd is equals to 0. P is equals to N plus Na. Now P is the majority carriers, N is the minority carriers. By using the Morse-Action law, we have to decide the minority carrier concentration. That means we know that Np is equals to Ni square is the Morse-Action law. Here P is the majority, we have to calculate minority carrier concentration by using Morse-Action law. So we have to replace P with N plus Na equals to Ni square, that is N square plus N into Na minus Ni square. So if we solve this quadratic equation, we will get N as minus, this is 1 by 2 minus Na plus or minus Na square minus 4 Ni square, which is option B is correct. In circuit, maximum reverse voltage across the diode is. So whenever the diode is reverse bias, this voltage is this and this is this. So reverse bias voltage across the diode is 2 into 24 root 2 minus 0.6, which is 67.282 volts, which is option B is correct. Figure shows a Zener diode regulator circuit whose Zener voltage is 24 volts and Zener resistance is 20 ohms. The power dissipated in the unknown resistor is. Here the power dissipated in the unknown resistor is nothing but current through the resistor and the voltage across the resistor. Voltage across the resistor Vx is nothing but 45 minus 24, which is equals to 21 volts. Current through the resistor is nothing but current through the Zener diode as well as the current through the load resistor. So Iz is given as 5 milliamps and IL is 24, that is 0.5 milliamps, that is 5.5 milliamps. So power dissipated across the resistor X is nothing but Vx into Ix, which is 21 into 5.5 milliwatts, which is nothing but here this is 2 milliamps, so this is 7, so this is 147 milliwatts. So option C is correct.